Hello, good morning. Okay. So, we can start. Uh, in the last lesson, we have seen the third step of life cycle assessment, the impact assessment method. In particular, we have said that each impact assessment method is structured into different steps, mandatory steps and optional steps. We have said that according to the ISO standard, the first step is the selection of impact categories. The second step is the classification of the inventory data in order to assign each data to the different impact categories chosen for our analysis. The third mandatory step is the characterization step, during which we have to convert each data into the unit selected for the impact categories. And then we have the possibility to apply the optional steps, normalization in particular, and weighting steps. These steps are useful to obtain a final single environmental score. With this score, we can compare different products in terms of their environmental sustainability. The idea is to use a reference scenario for the normalization step, by which we can convert our results into values without a specific dimension, without a specific unit. And then we can apply weights to each impact category in order to define which environmental impacts can be considered more important for our study. Then in the last lesson, we have seen the different kind of impact categories that we can choose for our impact assessment method. We have said that the impact categories can be divided into global, regional, and local according to the sphere of influence of each impact, of each environmental impact. We have said that also the selection of the impact categories depends on the aim of the study. Depends in particular, for example, if you want to use the LCA study for the evaluation of the environmental impact of a product for a company. The selection of the impact categories depends on the requirements by the commissioner of the LCA study. Instead, if we want to apply the LCA study, the LCA results to obtain an environmental label, in this case, we have to follow specific guidelines in which the impact categories are defined for each kind of product. Then we have seen the possible options, the possible different impact assessment methods that we could find in the CIMA-Pro software, in the commercial software for LCA. And so in the last lesson we arrived at this point as regard at this point where we have seen the example, an example about the characterization step. In this case, we have seen that if in our example we choose 3 different impact categories, in this case, climate change, acidification, and particulate matter, the aim of this step is the conversion of each inventory data to common units, a specific unit for each kind of impact category. So in this case, for climate change, the unit is typically kilograms of CO2 equivalent, and so each greenhouse gas, in this case CO2 and the nitrogen monoxide, is multiplied by a factor called as characterization factor. In particular, by applying this characterization factor, we can consider the different contribution of each compound, of each substance to the impact category. So in this case, CO2, for example, is multiplied by 1. In this case, the characterization factor is equal to 1 for CO2 because obviously the contribution of CO2 to this impact category, to climate change, corresponds to 1 kilogram of CO2 equivalent. But in the case of N2O, the characterization factor is higher than 1. In this example, 298, because the contribution of the nitrogen monoxide to this impact category is higher than CO2. So 1 kilogram of CO2 is not equivalent to 1 kilogram of N2O in terms of climate change, but 1 kilogram of N2O is characterized by higher contribution to this category. In the same way, we can replicate the same consideration, the same for the other impact categories. So for each impact category, we have to define the characterization factors for each substance, for each emission. After the characterization, we have said also, for example, about the characterization, we have said also that the definition of these characterization factors is not very easy. These characterization factors are calculated by using different models of the environmental mechanism. representing as realistically as possible the cause-effect chain of events. This is the idea behind the definition of the characterization factors. So these characterization factors are determined, are calculated by considering the cause-effect chain when a substance is emitted into the environment. For example, here you can see the cause-effect chain for a toxic chemical. In this example, we can read in this slide that the emission of this particular toxic chemical into the groundwater will allow it to flow into a lake where the chemical concentration might increase to a dangerous level. Then, after which fish could start dying, decreasing the overall fish population, and at last the fish species might go extinct. This is the first part of the cause-effect chain due to the emission of this toxic chemical. And in particular, this chain can continue because if we look to the end of the cause-effect chain, we can consider that we can arrive, no, as we can see in the figure, by starting from the emission of the toxic chemical into the groundwater, we can arrive at the end of the cause-effect chain. We can arrive to the final step about the extinction of species. If we look to this figure, and if we look to this cause-effect chain, we can consider that the impact category about this environmental aspect can be divided. We can define two different impact categories for this kind of situation. In LCA, we can define the so-called midpoint and endpoint impact categories. So between the midpoint categories, we find impact categories that consider the first steps in the cause-effect chain due to the emission of a particular substance. In this case, in this example, the midpoint impact categories, the midpoint impact category is the increased of chemical concentration in the lake. Instead, it's possible to define also endpoint impact categories. The endpoint impact categories instead consider the final step of the cause-effect chain. In this case, the extinction of species. When we analyze the different impact assessment methods in the software, we can have methods that consider only midpoint impact categories, excluding the final steps in the cause-effect chain, or we can have the possibility to have impact assessment methods with endpoint in impact categories. So in this case, these methods arrive to the final step of the cause-effect chain. Typically, in all impact assessment methods, the endpoint impact categories are only three. And typically, these three endpoint impact categories are named as human health, ecosystem quality, and resource depletion. In this example, if we consider this cause-effect chain, and if we consider the endpoint step, the extinction of the species can be considered as an impact inside the ecosystem quality endpoint category. Okay, so why? Which is the reason of these different classes, of these two different classes of impact categories, midpoint or endpoint impact categories? The reason is that the midpoint impact categories, in some cases, are more difficult to explain their meaning to the final user of the environmental results. In particular, previously we have seen different kind of impact categories. In this slide, these examples of impact categories are all examples of midpoint impact categories. All these impact categories are midpoint impact categories. For example, global warming, ozone depletion, acidification, eutrophication, water use, and so on. But if we use these impact categories to express the environmental burdens of our product, the main problem is that the final user of this result cannot understand very well the meaning of the results, because, for example, he cannot understand, for example, the meaning of acidification, the meaning of eutrophication. So it's not very easy to for the final user to comprehend the real significance of the environmental results from our study. On the other hand, probably the interpretation of the endpoint impact categories could be more easy for the final user of the results, because the endpoint impact categories, we have said that are human health, ecosystem quality, resource depletion. So probably the comprehends it's more easy in this case to the analysis of these results. But in this case, if we want to use endpoint results, the main drawback with this kind of representation of the environmental result is that by expressing the results in these terms, we can increase the uncertainty of our study because, as we have seen in this figure, um, the from a midpoint to end point, we have to consider other steps. In this case, for example, we have to model the fish population decreases due to the increased chemical concentration in the lake. And also we have to consider another step, the step between the fish population decrease, between the decrease of fish population to the extinction of species. So we add in our evaluation additional uncertainties to our model. So on by using, in summary, by using midpoint impact categories, we have um, less uncertainties, but we have the problem to have results that could be less easy to understand by the final user. On the other end, by expressing the results with the endpoint impact categories, we have the advantage to express the results in terms of endpoint, human health, ecosystem quality, and resource depletion that are uh, more easy to understand by the final user. Instead, we add more uncertainties to our study. Here in this slide, you can have a list of typical midpoint categories that we can find that we could find in the impact assessment methods. So you have a very long list. Some of these impact categories are known, but others um, are difficult to comprehend by the user. For example, here you can see the intermediate step between a midpoint to endpoint impact categories by applying a specific method, specific impact assessment method. This method is called as ILCD. This is one of the most used impact assessment method in the European context. In this case, you can see that which midpoint categories contribute to each endpoint category. So, for example, to human, I don't know, to natural resources, for example, natural resources to natural resources, only water use and resource use contribute to this endpoint category. In this case, the endpoint categories are named with different names. Previously, we have said that typically the endpoint impact categories are called as human health, ecosystem quality, and resource depletion. Here in this method, the three endpoint impact categories are defined, are called as human health, natural environment, natural resources, but the meaning is the same. So natural environment is equivalent to ecosystem quality. Natural resources is equivalent to resource depletion. So in this case, the method uses different names, but the meaning is the equivalent is the same. Okay. So then here you can see an example about the normalization step. In the table, you can see that in the previous slide, in the previous step, we have calculated the characterized results, in particular, for example, 2.49 kilograms of CO2 equivalent, and also other results for the other two impact categories. Then the aim is to divide this value. The aim is to divide in the normalization step. The aim is to divide the characterized results by the overall emissions in a certain region, um, in order to obtain a value, a pure value. In this case, the most difficult step um, to apply this normalization is that we have to define a reference scenario, a reference system. So in this case, we have to compare the environmental impact of our product to those of a reference system. I have said in the last lesson that typically for impact assessment methods, we use, for example, the overall emissions of greenhouse gases in Europe in 1 year per person. This is the reference scenario, but this reference scenario depends on the impact assessment method. So in this case, by this operation, we can convert characterized results into normalized results. For example, for climate change, if we divide 2.49 by 6,803 kilograms of CO2 equivalent per person per year, we obtain the final normalized results, 0.000366. Okay. So in this case, the normalization factor would be, I don't know in this case, but could be the global greenhouse gases emissions in Europe in 1 year per person. Okay. In the same way, we can define the other normalization factors, but the operation is the same. So we have to divide the characterized results by the normalization factor. At the end of this step, we have all normalized. We have normalized results, and these results are expressed in by the same unit. In this case, the unit is a person per year, but this is a pure number. Okay, person per year is not a very it's not a real unit. Okay, so the normalized results are pure numbers. We have the possibility to end our evaluation at this step, at the normalization step. In particular, if we end our analysis at this step, we have the possibility, by comparing the normalized results, we have the possibility to check which impact categories are more important for our product. In this case, for example, we can say that the particulate matter impact category is characterized by the most important impact for the analyzed product, because its normalized result is the highest. Uh, so we have also this possibility. But if we want to obtain a single environmental score uh, for our study, for our product, it's necessary to apply also the final step of um, the final step about the weighting of the results. Here you can see typical reference scenarios for the calculation of the normalization factors. So you have different strategies, but in each impact assessment method, different reference scenarios are considered. So it's not very important for us. Here you can see, for example, the normalized results for a product. In this figure, you can see the different impact categories considered by this impact assessment method. You have in this way, by the application of the normalization step, you have the idea of which impact categories are more important for this product. In this case, fossil depletion and climate change are the two most important impact categories. And also in this representation of the results, you can also find for each impact category the contribution of the different life cycle of the different life cycle stages of the product. So, for example, in this case, you have that the printing converter stage in the life cycle of this product probably is one of the most important stage, is the main contributor to the environmental burden of the product, as well as, for example, the label stock supply. Okay, these are the two main stages for this product. So we have said that if we want to calculate a final single environmental score, we have to apply the final step, the weighting step. In this case, we have to define weighting factors for each impact category. In this example, the weighting factor, for example, for climate change is equal to 23. For acidification is equal to 4.2, or 6.6 for particulate matter. So the mathematical operation in this case is very simple. It's very simple because we have to multiply the normalized results by the weighting factors. Then these results, these weighted results have to be sum each other in order to obtain the final score. In this case, 0.021. Here, you can see that to this number, 0.021, it's associated a unit, PT. PT is the acronym of point. Why in the LCA we decide to consider a unit for the weighted result. The weighted result in theory is a pure number for the previous reasons. It's a pure number, but typically if we arrive to the weighting step, this weighted result is expressed with this term points simply in order to try to increase the meaning, the comprehension of this result for the final user. So it is a sort of a conventional way to express the final result, but this unit does not have a specific meaning. So the idea is to when we apply the weighting step, the idea is to obtain a single environmental score. So if we arrive to this step, we have the possibility to compare two different products simply by comparing two values, two environmental scores. So the comparison is more easy in this case if we arrive to the weighting step. Instead, if we end our evaluation to the characterization step, the comparison will be more difficult because we have to compare 10, 15 environmental scores. And so it could be difficult to find and to define the best product in terms of environmental sustainability. But the main problem in this case, that we by applying the normalization and the weighting steps, we increase the uncertainties associated to our final results. This is the main drawback. In this slide, you can see the possible representation of the results after the weighting step. This figure can be obtained by from the software. In this example, we can see the different here. We can see the different stages of the life cycle of this kind of product. And with different colors, we can see the different impact categories considered by this method. These values are expressed in MPT, millipoints. Okay, so point multiply by 10 raised to minus 3. In this case, you can, the main result is that you can see which stages of the life cycle are most important for this product. In this case, label, stock supply, and printing converter, as we have seen in the previous example. And also we can see which categories are most important for this example. So in the following two slides, we can see which are the principal, which are the main methods used by the impact assessment methods to determine the weighting factors. Okay, so the possible question about the weighting step is how these weighting factors are determined, are calculated. So typically, we have four different options to for the calculation and for the definition of the weighting factors. Even if in the impact assessment methods in the software, only one of these four options is used, and in particular, the only option used is the last one. But I think that it's important, the last one, or the in some cases the third one, monetization. So the first two options are not very used, but it could be interesting to consider these two options. The problem is that these two options are very difficult to apply. So in particular, the first one is the distance to policy target. If we want to understand the meaning of these criteria for the calculation of the weighting factors, we can read this example in the slide. So, for example, if the goal for climate change is to reduce the national carbon dioxide emissions by 15%, and the goal for acidification, for example, is to reduce the national sulfur oxides emissions by 20%, the carbon footprint, so the climate change impact category, will get a higher weighting factor. So in this case, an issue with this approach is that policy targets may not reflect how serious problem actually is, because policy may be influenced by costs and other political considerations. So this approach could be interesting, but we have the problem that the weighting factors are based on policy targets, not and so in this case are not based on the real environmental burdens. So we could have we could have a problem in this sense. To avoid this problem, so if we want to apply the same method, but based on not policy targets, but on scientific targets, in this case, we can apply the second criteria, distance to scientific target. In this case, the weighting factors are based on scientific targets. But in this case, the problem is that it's very difficult to find scientific targets for all environmental impact categories. As we can read in this slide, for example, there is a general consensus that 350 parts per million is the maximum safe level of carbon dioxide in the atmosphere with regards to climate change. These safe levels are used as targets, but the farther away the current situation is from this target, the higher the weighting level. An issue with this approach is that not every environmental impact category has targets based on scientific data, and that the available scientific targets may not always be up to date. So this is the most important problem with these criteria, because for climate change, it's quite easy to find a target. It's more difficult to define or a target, a scientific target for other kind of impact categories. For example, acidification, eutrophication, or others. So the idea of these first two methods, policy, distance to policy target and the distance to scientific target, is to set threshold for each a target, a threshold for each impact category. And so, if, for example, in Europe, actually, we have an emission, we have emissions, so we have a concentration in the atmosphere of this kind of compound similar to target or lower to this target. So this impact category will be characterized by by a low weighting factor. Instead, if actually the environmental situation for this kind of impact is more critical, and so I don't know, the concentration of CO2 in atmosphere or is higher than the target. So in this case, the weighting factor for climate change impact category will be high. So this is the idea. So the weighting factors are calculated according to the distance to the targets. So in theory, these two criteria, these two approaches are the best options, but it's very difficult to apply to all impact categories. So for these reasons, we have the possibility to calculate the weighting factors also according to other two criteria, other two approaches. The monetization, the third one, and the panel weighting, the last one. About the monetization criteria is another interesting option, but also in this case, we can have several difficulties to to apply this method. In fact, in this case, the idea is to convert each normalized result, to convert each environmental impact into a economic value, into an economic value. In particular, this value can be based, for example, on the costs associated with preventing or repairing damage. One type of impact, as we can read in the slide, may be more expensive to prevent or fix than another. Another way to monetize an impact category is to measure how willing people are to pay to prevent certain impact. In fact, people might be willing to pay more to prevent impacts on human health than to prevent resource depletion. The idea, I repeat, is to convert each environmental burden into a monetary value, into an economic value. But the main problem with this approach is that it's very difficult to carry out this conversion, because it's very difficult to obtain an objective conversion of the environmental burdens into monetary values. So this criteria is very subjective, and this is the main problem. But also in the CIMAPRO software, we can find some methods that apply this kind of criteria. And this kind of criteria, for example, this kind of approach, it could be, for example, in use if we want to carry out not simply a life cycle assessment of our product, but it could be interesting also if we want to apply and to carry out a life cycle costing of the product. In the life cycle costing of the product, we apply the same approach as in the life cycle assessment, but in the life cycle assessment, we calculate the environmental impacts during the life cycle stages of the product. In the case of life cycle costing, we calculate the costs associated to each life cycle stage of the product. So the perspective is different and the aim is different, but in the life cycle costing, it would be interesting to consider, for example, not only the direct costs associated to the product, but it could be interesting also to consider the indirect costs of the product, and the indirect between the indirect cost of the product, we could consider also the environmental impacts converted into monetary values. So in this case, we have a better idea of the overall costs associated to our product. I repeat, by considering direct and indirect costs. So in this kind of application, the monetization criteria could be interesting for our case. The last one is in theory the most easy approach to obtain the weighted results. In this case, the approach is to simply ask a large group of people for their opinion on what is more important. So in this case, an issue with this approach is that the results can easily be skewed by the personal characteristics of the panelists. So different people have different levels of knowledge about environmental effects and different personal experiences with certain impacts. Typically, this approach is the most used in the impact assessment methods, but this approach is also in this case it's a subjective approach, no? But the idea is to define the weighted factors by considering the experience of different groups of people with specific knowledge in specific environmental impacts in specific environmental fields. Uh, the idea is to try to define weighted factors with a consensus between the different people. So this is the most used approach, but if we consider this approach, we can understand easily that if we want to apply the weighting step to our LCA study, necessarily we will increase the uncertainties of the associated to our final results. Okay, this is the main drawback. So, break of 15, 20 minutes about, okay? We can stop here
Okay.
for a break.
Okay.
Okay. See you later. Okay, we can start. So, so now it would be interesting to say something about uh, some of some impact categories. Uh, we have we have said previously that we have the possibility to select different impact categories to analyze by our study, but probably it could be interesting to explain the meaning of some of these environmental impacts that we can calculate by LCA. First of all, I think that it's important to explain the climate change impact category because and how the characterization factors are calculated for this impact category. Because this impact category is the most used category for the analysis of the environmental burdens of products. Um, Also, when an LCA study considers only this impact category, in fact, we have the possibility to analyze the results only considering one impact category. And if this unique impact category is climate change, the results that obtained from the study are known as a carbon footprint. So the carbon footprint is a typical LCA study by considering only the climate change impact category. Okay, so this is an important, very important impact in LCA. So I don't know if you know the environmental problem due to the emissions of greenhouse gases. In this slide, you can see a brief summary of the environmental problem due to the emissions of greenhouse gases. So we can say that the greenhouse gas effect, the greenhouse effect is a natural effect in our planet, in our atmosphere, and it is essential for the life on the Earth. In fact, without the greenhouse effect, the temperature, the average temperature of the atmosphere would be minus 18 degrees instead of 15 degrees. So the greenhouse effect is a natural phenomenon. Is a natural phenomenon, but the problem arises when we have a huge amount of emissions of greenhouse gases into the atmosphere. In fact, if we have a huge amount of emissions of greenhouse gases into the atmosphere, the main problem is that these gases can create a modification of the balance of the energy reaching the Earth's atmosphere from solar radiation and leaving it again from the Earth. This is the main problem. In fact, from the solar radiation, about the solar radiation, we can say that a fraction of the solar radiation reaches the Earth atmosphere. A fraction is reflected back into the space by the air molecules. And also this reflection, in particular, this reflection of the solar radiation into the space is due to a layer, as we can see in this slide, is due to a layer of greenhouse gases in the upper layers of atmosphere. So by the presence of this layer of greenhouse gases, we can maintain the temperature on the Earth's surface around 15 degrees during the year. So when the fraction of solar radiation instead reaches the Earth atmosphere, the Earth surface, this energy due to the solar radiation is in part absorbed by the Earth surface. So the Earth surface increases its temperature. And then during the day, this energy, a fraction of this energy is released back into the atmosphere as infrared radiation. Infrared radiation is a particular electromagnetic radiation characterized by a longer wavelength than the absorbed radiation. The absorbed radiation is the radiation from the solar radiation, okay? So a fraction of this energy absorbed by the Earth's surface is released back into the atmosphere. So now we have the problem about the huge amount of greenhouse gases in the atmosphere. In fact, the infrared radiation, this infrared radiation, is partially absorbed by greenhouse gases and therefore kept in the atmosphere instead of being released into the space. So in the natural situation, without any climate change, without any global warming problems, the energy associated to this infrared radiation can reach the space through this layer of greenhouse gases. When instead the concentration of when the concentration of these greenhouse gases is very high in the upper zone of the atmosphere, in this case, the problem is that the energy associated to this infrared radiation cannot reach the space and remain inside the atmosphere, and so could increase the temperature on the Earth surface. This is the main problem. This is the main environmental problem associated um, with the emissions of greenhouse gases into the atmosphere from anthropogenic activities. Okay, this is the main problem. So here, when we want to determine the characterization factors for this kind of impact category, as we have said previously, we have to define the cause-effect chain, no? So it's important to define the cause-effect chain. In this case, the cause-effect chain is summarized in this figure. So the first point is the emissions of greenhouse gases. Then we have the transport, transformation, distribution of greenhouse gases in the atmosphere. Then we have the disturbance of the radiation balance, which is the meaning of the disturbance of the radiation balance. The meaning is that by this increase of concentration of greenhouse gas in the atmosphere, we have said previously that we have disturbance in the energy balance, no? Because the energy associated with the infrared radiation remains on the Earth's surface and cannot reach the space. This is the meaning of disturbance of the radiation balance. This point could be of the cause-effect chain, could be considered as our midpoint. So when we refer to climate change impact category, we refer to this point of the climate, to this point of the cause-effect chain. So the climate change impact category reflects the environmental problem due to the disturbance of this radiation balance on in the atmosphere. But if we want to continue to analyze the cause-effect chain, in this case for climate change, after this point, we have the increase in global temperatures of atmosphere and surface. Then we have the increase in sea level due to heat expansion and the melting of land-based ice, the increased water vapor content of the atmosphere causing more extreme weather, and at last we arrive to the negative effects on the ecosystems and the human health. And so by analyzing this cause-effect chain, we can say that for climate change, we have two endpoints. In particular, climate change has an influence on both human health and ecosystem quality endpoint impact categories. Then we can we can define how the characterization factors are calculated for this category. In this case, first of all, we can say that the characterization factors, the characterization factor for this impact category is called as global warming potential. So each greenhouse gas will be characterized by a different global warming potential. And how is defined, how the global warming potential is defined? The definition of the global warming potentials for the different greenhouse gases is based on this equation. So now it's not important, obviously, to uh, uh, analyze in detail this mathematical expression, but it could be interesting to understand how this characterization factor is determined. In particular, for each compound, for each greenhouse gas, um, the corresponding global warming potential is calculated by the ratio between the disturbance of the substance of the compound, the disturbance, as we have seen later previously, the disturbance of the radiation balance generated by the emission of a certain greenhouse gas, divided by the disturbance of to the radiation balance of the CO2. So the global warming potential is calculated by comparing the disturbance effect of a certain greenhouse gas, then the disturbance effect due to CO2. This is the meaning, okay? And when we want to compare the different contribution to the disturbance of the radiation balance of two different greenhouse gases, CO2, and for example, I don't know, one other typical greenhouse gas is methane, we have to consider, as we can see in this equation, we have to consider not only the concentration of gas of the gas in the atmosphere, but we have to consider, for example, its effect on the disturbance of the radiation balance. In this case, the parameter A takes into account the specific effect of each compound on the disturbance of the radiation balance. And also we have to consider another parameter, the parameter T, that is the number of years during which, for which the phenomenon is considered. In fact, when we refer to the global warming potential of a substance, we have to say that each compound, each greenhouse gas could transform itself during the time. Each substance, for example, a molecule of methane, a molecule of another kind of greenhouse gas, I don't know, N2O, the nitrogen monoxide, and so on. These molecules during time, during the years, don't remain in the same state, but they could convert, they could be transformed by chemical reactions into other compounds, and these compounds, for example, could not be greenhouse gases. And so when we want to calculate the global warming potential of a substance, it's in all cases, it's important to define in which is the reference period of the analysis. And in particular, when we refer to the climate change impact category, in all impact assessment methods, we can find three typical temporal scenarios. In particular, we can have three temporal scenarios: 20 years, 100 years, and 500 years. So if we open the CIMAPRO software and we analyze the climate change impact category inside an impact assessment method, we can find that this impact category, we can find that we can have three different options for climate change impact category: climate change at 20 years, climate change at 100 years, and climate change at 500 years. By starting from these considerations and from the definition of the global warming potential, we can say that for us, for climate change, typically the unit is kilograms of CO2 equivalent. So equivalent, the meaning of equivalent is that we compare each greenhouse gas to the effect of CO2 on the disturbance of the radiative balance in the atmosphere. This is the meaning of equivalent. And for this reason, each characterization factor is expressed as kilograms of CO2 equivalent divided by kilograms of the compound, kilograms of the greenhouse gas. In this way, if the global warming potential is equal to 1 for a substance, the meaning is that its contribution to the disturbance of the radiation balance is equivalent to the disturbance due to the same amount of emission of CO2. Okay, so 1 kilogram of the compound is equivalent, in terms of climate change, is equivalent to 1 kilogram of CO2. Instead, for example, for methane, this number is different, is 28 kilograms of CO2 equivalent divided by kilograms per kilogram of methane. For the nitrogen monoxide, this number is equal to 310, for example, depending on the method. For other methods, we can find, for example, 298 and so on. But this is the idea. And but these characterization factors are the same or are different if we change the reference years of the evaluation. The ask to this question is that the characterization factors, and so the global warming potentials of the greenhouse gases, depend on the reference temporal scenario, the reference temporal years. Why? The reason and the ask to this question is reported in this table, where we can see the global warming potentials for different substances, for different greenhouse gases at different years. So, for example, if we consider, I don't know, methane, in the case of methane, we can see in the table that the lifetime of of methane in the atmosphere is equal to about 12 years. Okay, after 12 years, so if we have today an emission of a certain amount of methane, the molecules of methane remain in the atmosphere for 12 years. Then, after this period, methane is converted into other compounds without climate change, without any effect on climate change impact. If we consider the lifetime of methane, 12 years, we can understand the reason of the different global warming potential for methane with different temporal scenarios. In fact, if we consider 20 years for our temporal scenario, in this case, we can say that for 12 years, we have a contribution on the climate change by this emission of methane. And only for 8 years, 20 minus 12, only for 8 years, we don't have any contribution to this environmental impact because the molecule of methane will be converted into other substances. Instead, and so in this case, in this example, the global warming potential of methane for 20 years is equal to 72. But if we consider, for example, global warming potential at 100 years, we have a significant change to this situation, because in this case, only for 12 years, we have a contribution to the climate change, but then we have 100 minus 12 years, so 88 years, during which we don't have any contribution to climate change due to this emission, due to this substance. And for this reason, the global warming potential, that is an average effect between the first 12 years and the remaining 88 years, the global warming potential at 100 years for methane will be lower than the global warming potential at 20 years. This is the reason of different characterization factors for the different greenhouse gases. For the same reason, the global warming potential at 500 years will be lower than the value for 100 years. Okay, this is the same. And this reason is valid for all substances. In summary, we have to consider a sort of dilution effect during the time, a dilution effect of the substance during the time. In the table, we can see the main, the most important greenhouse gases, but we can have other greenhouse gases that are counted in an impact assessment method. But these are the most important typically. One one problem, one question could be what time frame should we use? What time period we have to use when we decide to analyze climate change impact? The time frame depends on the aim of the study. Typically, the most used time frame is 100 years. This is the most used time frame. But the choice depends on the aim. In fact, as we can read in this slide, if the goal is reduce global warming by 2035, maybe 20-year global warming potential might be most appropriate. But if the goal is to decrease global warming potential by 2115, maybe 100-year global warming potential might most appropriate. So we have to choose the time frame according to the aim of the study. Other important consideration about this impact category is how we have to treat the biogenic carbon dioxide emissions. In fact, when we carry out an LCA study, and when we calculate the results in terms of climate change by applying an impact assessment method, the software allows us to divide the greenhouse gas emissions between fossil emissions and biogenic greenhouse gas emissions. Which are the differences? The difference is that biogenic greenhouse gases are emitted, are released from biological processes, okay, from living materials. These kind of emissions, of biogenic emissions, are, for example, due to the wood combustion, for example, are due to for example, the disposal of municipal waste into a landfill. If we put organic waste material into a landfill, from the landfill we have the production during the years of an amount of methane due to the anaerobic digestion process inside of the organic material inside the landfill. Biogenic greenhouse gases are released from biological processes. So it's important to divide when we analyze and when we interpret the results of the LCA study in terms of climate change. It's important to divide the fossil and the biogenic greenhouse gases. Also, because the biogenic greenhouse gases, in theory, these emissions often are assumed to have a net zero release of greenhouse gases. Why? The reason is that the CO2, the greenhouse gases released by a biological process, is recaptured during the regrowth of the biomass from which for example, if we consider the wood combustion, the CO2 from wood combustion is the amount of this CO2 is equivalent, is the same of the CO2 absorbed by the plant during its life. It's important to distinguish, to separate, to divide biogenic and fossil CO2 for this reason, because in theory, biogenic greenhouse gas emissions are less important than the fossil greenhouse gas emissions. But we have a problem if we consider the time lag between emissions and regrowth of the plant. In fact, if we consider the 20 years scenario for the calculation of the global warming potential, probably in this case, during this time period, during this time frame, we have the release of CO2, for example, but during the 20 years, we don't have the possibility to reabsorb this amount of CO2 by the plant because the absorption of this amount of CO2 by the plant requires more time than 20 years. And so, for this reason, when we want to analyze the climate change impact category, it's important also to consider this aspect. Typically, if we consider 100 years, we don't have this kind of problem because 100 years is a time frame sufficient for the reabsorption, the recapturing of the CO2 by the plants. But if we consider 20 years as our scenario, we could have this kind of problem. And so in this scenario, the biogenic greenhouse gases, the biogenic greenhouse gas emissions should be added to the fossil greenhouse gases emissions because they are not recaptured during this time frame. In the next slides, you can see, you can have different, the explanation of different of the most used impact categories, but for us, it's not important to analyze in detail all impact categories. But I think that we can see another impact category that is the stratospheric ozone depletion. Also, this category is one of the most used category when we decide to carry out an LCA study. So I think that we can see only these two, climate change and the stratospheric ozone depletion. As regards this category, first of all, we have to say that we have to say something words about ozone. Ozone is a highly reactive and unstable molecule. And in particular, this molecule is present in lower atmospheric layers, in particular in the troposphere, and in larger concentration in stratosphere. Stratosphere is the layer of atmosphere between about 12 to 15 kilometers. Okay, atmosphere is divided typically in different layers. So the first layer is troposphere, then we have stratosphere. So typically ozone is present in troposphere in low concentration, and in stratosphere in larger concentration. This is the situation. But we can say that in the troposphere, ozone is considered a pollutant in the troposphere. Okay. Instead, in the stratosphere, ozone is useful for the life on the Earth, on the planet. So it's important to decrease the ozone concentration in troposphere. It's important to increase the ozone concentration in the stratosphere. This is the situation. And according to this situation, we can have two different impact categories. One referred to the stratospheric ozone, and one referred to the tropospheric ozone. So in this case, if we have a large concentration of tropospheric ozone, the main problem is that this ozone can have harmful effects on humans, animals, plants, and materials. Instead, about the stratospheric ozone, in this case, this ozone is very important for the life on the planet Earth due to its capacity to absorb energy-rich UV radiation, preventing destructive amounts of it from reaching life on the planet's surface. And so, typically in impact assessment methods, we can have two different kind of impact categories about this theme: stratospheric ozone depletion or diciamo, the other the impact category associated to the tropospheric ozone has different names in impact assessment methods. One of these, for example, is photochemical ozone formation, smog formation, and so on. We can have different names, different terms for the tropospheric ozone. In particular, as regards the stratospheric ozone depletion, first of all, we have to say that the solar radiation is divided into different wavelengths, and according to the wavelength, we can divide the solar radiation into three classes: ultraviolet radiation, visible radiation, and infrared radiation. And the ultraviolet radiation is the most dangerous radiation for the life on the Earth, on the Earth's surface. Okay. Ultraviolet can be divided into other three classes: UVC, UVB, and UVA. In particular, UVB is of the most concern due to ozone layer depletion. Okay. So if the concentration of stratospheric ozone decreases, the UVB fraction of solar radiation can reach the Earth's surface, generating some problems on human health, ecosystem quality in particular. In fact, the impacts due to this fraction of solar radiation on human health are, for example, suspected to include skin cancer, cataracts, sunburn, increased skin cell aging, and so on. Irritation, for example, to the respiratory passages. Also, this UVB fraction has important impacts on the ecosystem quality, because the effects are, for example, the epidermal damage to animals. Also, radiation can damage to the photosynthetic organs of plants, causing reduced photosynthesis, leading to lower yields and crop quality in agricultural produce. So we have several different damages due to this fraction of solar radiation. In this slide, we can see how the ozone molecules are destroyed by something compounds in the atmosphere. So it's not important for us to understand the chemical reactions, but we can say that, for example, the most dangerous emissions for this kind of impact are the so-called chlorofluorocarbons. These substances, when they reach the stratosphere, can react with the molecule of ozone. And so in this way, the ozone is destroyed, and it's converted into other compounds, oxygen and some chlorine radical. So in this way, we have the destruction of ozone molecules in the stratosphere. So it's important to avoid the emissions of these substances, of these chlorofluorocarbons into the atmosphere in order to avoid this problem. Chlorofluorocarbons are in the past were used in refrigerators, air conditioning, heat pump systems, but in the most recent years, and in particular from after the Montreal Protocol in 1980, I don't remember exactly the year of the Montreal Protocol, but most of these ozone depleting substances were phased out. But the problem is that the influence, the main problem is that it will take some time before the ozone depleting substances disappear completely from the atmosphere. So actually, we have the problem of the stratospheric ozone depletion due to the previous emissions of these kind of compounds. Also, another substance that can create an environmental problem in terms of depletion of stratospheric ozone is the emissions of dinitrogen monoxide. In this case, dinitrogen monoxide is one of the the most typical emission in the agricultural sector when we apply on the field nitrogen fertilizers. A fraction, in this case, a fraction of nitrogen is in the fertilizer is oxidized by the oxygen in the air, and a fraction of this nitrogen is released into the atmosphere in the form of the nitrogen monoxide. And so this is an important problem. Here you can see the cause-effect chain in order to calculate the characterization factors for this kind of impact category. Also, in this case, we can reach um, the endpoint effect. Also, in this case, as for climate change, we have the influence on two endpoint impact categories, on human health and on the ecosystem quality. Here, instead, you can see the characterization factor for this impact category. In the previous one, we have said that the characterization factor is known as global warming potential. In this case, instead, the characterization factor is called as ozone depletion potential, but it is calculated in the same way as for the global warming potential. In fact, is obtained by comparing the effect on the depletion of stratospheric ozone due to by comparing the effect of a substance of an ozone depleting substance with the ozone depleting effect of a reference compound. In this case, the reference compound is CFC11. CFC11 is the reference compound for the calculation of the characterization factor. So for climate change, the reference compound is CO2. In this case, the reference compound is CFC11. And so in this case, the typical unit for this kind of impact category will be CFC11 equivalent, okay? So for climate change, kilograms of CO2 equivalent, in this case, kilograms of CFC11 equivalent. Okay, then you can see here the meaning of other impact categories, but it's not important to see all impact categories, but you have the possibility to read. In conclusion, we can say that each impact assessment method considers different impact categories. Each impact category will be characterized by different characterization factors. And also in each impact category, you could find, for example, the same impact category, but the characterization factors could not be the same because they are calculated in a different way by different assumptions. Also, the unit of the same impact categories could be different between each impact assessment method. So by changing the impact assessment method, the final results can change, obviously, because the method is made on different basis, is made on different hypotheses, is made on different methods for the calculation of the characterization factors. So it's important to define at the beginning of the study, it's important to define which impact assessment method is better for our study, depending on the aim of the study. Here you can see one of the most recent impact assessment method, Recipe 2016. This method is one of the most used methods in literature. This method is consider 18 midpoint impact categories and 3 endpoint impact categories. The same: human health, ecosystem, resource depletion. So this is not important now to see in detail the recipe method, but here you can see the different units for the midpoint categories, and also you can see the units used for each endpoint impact category. Okay, so we can stop here. So next Wednesday, you will have the lesson with my colleague Lorena Foschi. With Lorena, you will see the CIMAPRO software with some examples. And then on next Friday, we'll have our last lesson for this first part of the course. So in the last lesson, we'll finish to see the last step of LCA, the interpretation step, and then we'll see briefly the different types of environmental labels with a particular focus on the third type of environmental label, that is the environmental label based on the life cycle, based on a life cycle assessment. So this is the program, and so next week we'll finish this first module of the course. Okay. So for us is for today it's all. Bye bye.
Thank you. Bye bye.